welcome to LeChatelier's principle. What is important to understand about equilibrium shifts before we talk about them is where we left off with equilibrium last time, which is that reactions have not stopped. So no, reactions have not stopped. At equilibrium, concentrations remain constant because the rates of two reactions are equal to opposing processes, I should say. So what actually is going to happen today, we're going to talk about shifts in equilibrium, which actually mean that we're going to have one direction of the reaction, either a forward or reverse reaction, get favored over the other direction. Favored means that one rate will increase and the other will decrease. So if we imagine this system at equilibrium that we've been talking about, if I were to add more O2 to this reaction, so O2 is right here, it's one of our reactants. If I add more O2 into my vessel up here, what this is going to do is it's actually going to cause more collisions between SO2 and O2. So we have to keep in mind, if I add more O2, O2 is going to react with SO2. What this means in terms of collision theory, O2 is more likely to react with SO2. So this reaction is more likely to occur. What this is actually going to do for me is it's going to increase the rate of SO2 reacting with O2 and forming SO3. However, it is not going to affect the rate of the reverse reaction. So what ultimately will happen is I'll increase the concentration of SO3 going on, but the rate of SO3 decomposing back down to SO2 and O2 is not initially affected. Now, over time, there's going to be an equaling out that's going to occur, but we're really focusing on what happens right when we add stuff. So if I add more SO2, it's going to cause more collision, or I'm sorry, more O2, it's going to cause more collisions with SO2, therefore increasing the rate of this reaction and increasing the amount of SO3. So this is described as LeChatelier's principle. LeChatelier's principle predicts how a chemical system will react to a change. A change in conditions can be called stress. Just like changes in your life cause stress, this happens to systems at equilibrium as well. For example, if all of a sudden your calculator batteries died, this would be a stressful situation. It is a change for you. Some of the things that are going to affect our equilibrium and possibly shift it are changes in concentration, temperature, and volume of pressure. And those will really only be true for gases. Equilibrium will shift to counteract or relieve the stress. What this means in terms of a reaction shifting is we're going to have a reaction get favored, either the forward or a reverse reaction. So either the forward or reverse reaction will increase in rate. So at equilibrium, our concentrations were constant and our rates were equal. The rates of one of the processes will now be sped up. So there are four factors that can affect equilibrium or cause this shift. So again, these four factors are causing what we call stress. I will be using the abbreviation of brackets to mean concentration. So whatever's inside of there, that just means the concentration of whatever that species happens to be. So let's take a look at this reaction right here. If we have H2CO3 breaking down into carbon dioxide and water, if we were to add more H2CO3 to this, what this is going to do, since I'm increasing the amount of this that I'm adding, is I'm going to have more of that to decompose to CO2 and O2. So this is going to increase the rate of the forward reaction. In other words, I'm going to favor my forward reaction. Because I'm favoring this stuff happening, I'm going to now have an increase in CO2 and an increase in H2O. Now, on the other hand, and I'm not really going to worry about my concentration of what it is that I am changing. I'm only going to worry worry about things that are affected by the system. On the other hand, what happens when CO2 is added? So if I were to add CO2 here, this is not going to affect the rate at which H2CO3 breaks down. So what's going to happen instead, I'm going to have more CO2 able to bump into H2O and therefore cause more collisions. So they're going to collide more, driving my reaction this way. So this is going to increase the rate of the reverse reaction. Or in other words, favor the reverse reaction. I am therefore going to have an increase in H2CO3. Now, because I did not change how much H2O I'm putting in there, the CO2 is going to react with H2O, react with H2O, react with H2O, and it actually can begin to use that H2O up. So I'm actually going to have a decrease here in my concentration of H2O. Now, on the other hand, I can also remove things from my reaction vessel. So imagine, if you would, that I remove H2CO3. Now, if I continue to remove this from the reaction vessel, it's not present to decompose into CO2 and O2. So what's actually going to happen, these two will keep reacting. However, we have a drastic decrease in the rate of the forward reaction. So what's actually happening here is I'm increasing the rate of the reverse reaction. In other words, I'm favoring the reverse reaction. What's happening because of that is, as I'm removing the H2CO3, the system's trying to replace it. While this system's trying to replace it, CO2 and H2O keep reacting, and turning into that. However, I'm not replacing them. I'm not doing anything to help those guys. So again, I'm not going to worry about talking about the H2CO3 since that's what I changed, but I am going to have a decrease in my concentration of CO2, and I am going to have a decrease in my concentration of H2O, as they work and react to try to replace what we're removing from the vessel. Now, on the other hand, if I were to remove CO2, so going back into my reaction up here, and we're going to imagine what would happen if I took out CO2. By removing CO2 from the vessel, CO2 would not be present to react with H2O. So what would actually happen here is we would have this reaction, this forward decomposition still occurring. However, we would have a drastic decrease in the amount of CO2 and H2O colliding going back in the other direction. So what happens here is I'm going to increase the rate of the forward reaction. And when I say increase the rate here, I'm really talking relative to the other reaction. In other words, I'm favoring forward reaction, or shifting to the right. As I remove that CO2, I'm not going to talk about CO2's concentration, I'm manipulating that. But the reaction is going this way and making more H2O, which doesn't have CO2 to react with. So therefore, I'm going to have an increase in my concentration of H2O. So building up in the vessel has nowhere to go. And I'm going to have a decrease in my H2CO3 because that's still decomposing and turning into H2O and CO2. I'm just sucking that CO2 out. And this is just a visual of this, so you can see if we were to add, for example, more CO2, we're likely to have more and more CO2s available to react with H2O. As those CO2s and H2Os react, they're going to form more by H2CO3. If I were to, for example, take H2CO3 out, I'm able to have these guys break down and make H2CO3, but I can't make new water or new carbon dioxide to replace them. Temperature changes also cause shifts as well. This is going to happen when we have heat terms in the reaction. So we do need to identify where our heat term is. So a reversible reaction is exothermic in one direction and endothermic in the other direction. So if I were to increase temperature on this system, this is like adding heat. When we add something on one side of reaction, helps that reaction happen more. By adding heat here, we are actually helping SO3 to decompose. So this is actually going to favor my reverse reaction. In other words, it's going to increase reverse reaction rate. As that occurs, I'm going to have a decrease in my SO3. It is getting decomposed into SO2 and O2. I'm going to have an increase in my SO2 and an increase in my O2 since I'm favoring the reaction that is making those. So I'm using up my SO3, turning them into SO2 and O2. Now, imagine on the other hand, we remove heat. So if we were to remove heat, we would be decreasing the temperature. If we remove heat, it's going to really reduce the rate at which the SO3 gets broken down. By removing heat, what we're actually doing is favoring the reaction of SO2 and O2 to turn into SO3. It's almost like we're favoring them making more heat to kind of keep us warmer or something like that. So if we decrease temperature, we're removing heat. In this case, we're going to favor the forward reaction. In other words, we're going to increase the rate of the forward reaction. As we're doing that, SO2 and O2 will react at a faster rate, and they're going to get used up because they're being turned into SO3. So we're actually going to decrease our amount of SO2. We're going to decrease our amount of O2. We're going to increase our amount of SO3, which is not getting decomposed as readily back into SO2 and O2. Now, pressure and volume, I like to say they ain't nothing but a G thing. These will only affect your gases, so you need to identify how many moles of gases you have in a particular system. So our moles of gases actually don't really have to do with our little tiny subscripts down here. They have to do with the numbers out in front. So in this particular reaction, we have an invisible 1 here that we don't write, so that's indicating 1 mole of gas right there. We have a 3 right here, and again, we have these G's telling us when things are gases, so this is 3 moles right here. And on this side, we have 2 moles of ammonia gas. So in this particular system, what I can see is on the left side I have 4 moles of gas, and on the right side I only have 2. So I'm just going to kind of get this out of here so it doesn't get too messy. But this side of the reaction has 4 moles of gas, including both of my reactants. And this side has 2 moles of gas. So changing pressure only affects gases. At high pressure, we want to shift the system to the side that is going to have fewer moles. At low pressure, we're okay to let things spread out and have more moles. If you imagine you move to a very tiny apartment, you would condense all your stuff together. However, if you move to a huge house out in the country, you could let yourself spread out all over your house. That's what's going on here. So if we increase the pressure on this system, we want to go to our side with fewer moles. Our side with fewer moles is over here, 2 mole side. So essentially what's happening, just to show you a little visual of this, we have the same number of atoms because of the law of conservation of matter. We can't lose anything. But this side over here has 1, 2, 3, 4 moles of gas. We took those atoms and we rearranged them so they only fit in 2. So they fit into 2 moles over here. So that side's going to take up less space. So when we're at higher pressure, we're going to be favoring the forward reaction. So we've kind of squished everything down. And because of that, we're increasing the amount of NH3. That takes up less space. We're decreasing the amount of H2, and we're decreasing the amount of N2 as they turn into NH3. On the other hand, if we decrease our pressure, we're able to allow our system to spread back out to its 4 mole side over here, or we can take up more space if we want. So in this case, we're going to favor reverse reaction. We're going to have an increase in our concentration of N2, an increase in our concentration of H2, and we're decreasing our amount of NH3. Now, very often, we actually have a little helpful picture we can draw that I want to show you guys. This is kind of a Mr. Irby thing, and it works pretty well. We know we have 4 moles over here, as we talked about in the last slide, 2 moles over here. So to give this a little bit of a representation, you can take your bigger mole side, kind of draw a big circle around it. So 4 moles takes up a lot of space. If we continue this over here, 2 moles takes up less, so we make that side take up a little bit less space. What we can do now is we can visualize if we were pushing on this, if we're pushing on it down, putting it under high pressure, we would send it that way. If we allow the system to relax and spread back out, we would send it that way. Volume does affect pressure. Very often we want to change pressure. We do so by changing volume. So if we increase volume, we allow everything to spread out, we are actually decreasing pressure. So if you imagine on that picture that we drew on the last one, a big volume is that left side where it's very large and spaced out. So if we increase the volume, we're decreasing pressure. So what we would expect to happen here, this is the same reaction. We got our 4 moles on the left and our 2 moles on the right. If we're decreasing our pressure here, we're going to shift. I'm sorry, stick with favoring. We're going to favor our reverse reaction. So we're going to shift towards our side with more moles, thus increasing the concentration of N2, increasing the concentration of H2, and decreasing the concentration of NH3. Decreasing volume, squishing things together, it's going to increase our pressure. So if we now have a smaller reaction vessel, we want to shift toward or favor our forward reaction. That allows us to have, that'll give us fewer moles, that'll kind of fit better, if you will. So this is going to increase the amount of NH3 we have on our fewer mole side and decrease our amount of H2 and decrease our amount of N2. To wrap this up, there is some terminology that's important. When we favor a reverse reaction, we can also call this shifting. In other words, the forward reaction is going this way. We can call this shifting to the right. A reverse reaction goes back in the other direction. This is considered to be a shift to the left. And often we can just show these with arrows in the worksheets that we do. We utilize that to make them a little bit quicker to do. So if we're favoring forward, we're shifting right. If we're favoring reverse, we're shifting to the left. And that just means that we have an increase in the reaction going in that particular direction on the page. There's a general rule that I find really, really helpful. And that rule is add, away, remove, towards. Anytime we add anything to a system, so if we add heat to a system, we will shift away from the heat term in that reaction. If we add a reactant or a product, we'll shift away from that reaction in that system. If we remove something, it's almost as if the system needs to replace it, so we shift back towards that thing that we removed. So you can go and put your finger on a reaction and say, hey, I removed this, I've got to shift towards it. We'll talk about that a little bit in a separate video when we go through some examples.